This is part 2 of a series of videos on the origin of the elements. In part 2, we're going to start getting into nuclear fusion. So let's start by revisiting the Big Bang. The universe started a little under 14 billion years ago, and it started with a Big Bang. After 3 minutes, we had hydrogen, helium, deuterium, tritium, a little bit of lithium. But then the universe had expanded so much that no more elements could be made. So this begs the question, how are elements made and why did they stop being made? So let's talk about hydrogen fusion. First thing I want to do is to show you a little video of how hydrogen fusion works. So we have what's called the proton-proton chain reaction. That's because hydrogens are just protons when they don't have the electrons. Here we have two, they came together, they made a deuterium by converting one of the protons into a neutron. So now we have a deuterium and a proton, they come together, and now we get a helium. Now we've got two heliums that have one neutron each, and they come together and make a helium-4. So we have this reaction that's basically 4 hydrogens, and it goes to making 1 helium. So here you can see that same proton-proton chain reaction as a static image. We've got 2 hydrogens, they come together. One of the hydrogens is just a proton, stays a proton. The other one gets converted into a neutron by ejecting a positron. That's an anti-electron, and it also ejects a neutrino. Same thing is happening here. Now we've got 2 of those, so we're going to bring them together with another proton each. So we've got hydrogen here, they're coming together, and we get now 2 protons and 1 neutron, that's helium-3, and we have another one here. And then we're going to bring those 2 together, and in bringing those together, we can get just 2 protons and 2 neutrons, which is a helium-4, and it ejects 2 of those hydrogens. So, and along the way, we produce neutrinos. That's these little V-nu looking things. That's what happens when we throw out the positron. We also release some energy here, and that's the energy that's created by nuclear fusion, is these gamma rays that are being thrown out as a part of the process. Here we have those same reactions that we just saw in the video in the previous slide. But now we can see some other reactions that can happen. So here I've got a deuterium, that's the same as this one. I add another neutron and I get a tritium. That's a hydrogen with 2 neutrons. Here I've got 2 deuteriums, so that's a deuterium. I've got 2 of those. I can stick them together and end up with a helium with an extra neutron being thrown out, and then that neutron can be used for further reactions. If I've got a helium, I might be able to add another hydrogen to it, another proton, and that will give me a lithium, and so on. If we can just keep adding things, then why does it stop? Why don't we make bigger elements than things like lithium and just a little bit of beryllium? And the answer is the repulsion of the particles. Remember, these are charged particles. Just like electrons are negatively charged, the protons are positively charged. And when you try to push them together, they're going to try to push apart. If you ever tried to push 2 north poles of magnets together, they try to push apart. If you put the north and south pole together, they come together really hard. But if you try to push the 2 north poles or the 2 south poles together, they will push themselves apart. It's a similar sort of effect when you've got 2 like electric charges. When you try to push positive charges together, they will push apart. And that's shown here that when they're not moving very fast, the reaction of being pushed apart, they will deflect each other. So it's like you're trying to bring the 2 magnets together, but it's pushing apart. And if you bring them together fast enough, you might be able to hit them to each other. But if you're not bringing them together fast enough, they will deflect. And so that's the same thing that's happening with our protons. You're trying to bring them together, but they deflect. But if you bring them together fast enough, then you can actually get them close together. Once they're close enough together, then there's a new force called the strong force that comes into play and binds them together. Okay, so let's get into this in a little bit more detail. In order for those 2 nuclei to get together, that's 2 nucleuses, so in this case 2 protons. For any element, you're going to have a charge on your nucleus, which is E, which is the charge on a single proton, times the atomic number. Remember that the number of protons gives you the element. So Zi is the element, ith element, and E is just the charge on a proton or electron. Now, when we try to bring them together, they have a force that's pushing them apart. And so the Coulomb repulsion that's pushing them apart is given by this equation. Don't worry about this in too much detail, except that what matters is how big is the element, how much charge does it have? So that's, if you just have something like hydrogen where Z is just 1, then Z1 and Z2 are both 1, and Z1 times Z2 is just 1, and so this is just 1. And then how much energy there is pushing them apart is dependent on how close together you get them. But if you go to bigger elements, then you're going to have, say, for helium, you've got 2 times 2. Or for lithium, you've got 3 times 3. And so as you go to bigger and bigger elements, it's harder and harder to bring them together. So just to summarize what I just said, like charges repel. So as you try to bring them together, they will just push apart. The nuclei are positively charged, and big nuclei, that is to say, elements, the atomic number defines how many protons they have, and that defines how much positive charge they have. You need very high densities and very high temperatures. High temperature is basically a measure of the average speed of the particles. So the air in the room that we're in, all of the molecules are moving at different speeds, but the average speed gives us the temperature in the room. And so the temperature is really a measure of how much energy the particles have got, how fast they're moving. And if you don't have high density, they just don't get close enough together. So you need both high temperature for them to be moving fast, and you need high densities for them to get close to each other. So if you can bring them close together and you can do that fast enough, then you can make a reaction happen. But how high a temperature do you need? Well, let's do a rough estimate of that. So the strong force, the thing that will hold them together once they get in close enough, only works over about 10 to the minus 15 meters. That's a teeny tiny distance. That's 0.000000000000000001 meters. It's teeny. So, but that means that that's the distance between the atoms. That's this R distance right here. If we put in the right numbers, so this C here, it's just a constant. That's this 10 to the minus 9. The charge on a proton is this number here in coulombs, 1.6 times 10 to the minus 19. The Z1 and Z2 are the atomic numbers of the elements you're trying to bring together, and this is the distance you're trying to get them together. So if you put in all those numbers, and then let's say that this is for hydrogen, then the Z's just go to 1, then we get an energy that you need these elements to have of about 10 to the minus 13 joules. That might not sound like a lot, but in terms of temperature, it's a lot, and we'll get into that in a second. Remember that if you go up to, let's say you want to stick 2 heliums together, now Z1 and Z2 are both 2, and so it'll be 4 times more energy that's needed. So how much energy do atoms or nuclei have when they're in a gas? The average kinetic energy is given by this equation. So what you have is, this is the temperature, this is a constant called a Boltzmann constant, and this is the kinetic energy. So we can work out what temperature do we need them to have in order to actually have the right temperature to overcome this Coulomb barrier, this thing that's pushing them apart. So all I've done is to rearrange this equation. I've got T equals 2e over 3k. And so now I've got the energy I need is this 2.3 times 10 to the minus 13 joules, and everything else is constants. And that means that it's of the order of 10 to the 10 Kelvin. Kelvin are not a very intuitive unit, but it's about the same in Celsius, and it's about twice as much in Fahrenheit. So again, it's about the same number, regardless of which units you're working in. It's over 1 billion Kelvin. This works in that very early universe when everything's very hot and dense, but it spreads out very fast. And even the core of the sun is not this hot. The core of the sun is only about 15 million Kelvin. And that's where it's doing some of this fusion. We'll come back to that in a future video. Okay, so what's actually happening inside of the sun? The average kinetic energy of a particle is given by this equation again, and my temperature is about 10 million Kelvin. So if I put it in, it's only about 1.3 keV, or 10 to the minus 16 joules. That is 1,000 times too small for them to be able to come together. So the energy is not enough. They're not moving fast enough to be able to come together. So what's going on? How do we actually make this happen? Well, it turns out there's this entertaining thing in quantum mechanics called tunneling. There'll be a separate video that goes into this in detail, not for the faint of heart, but basically tunneling is, you can basically show that when we think of the particles as also waves, we can have them break through this barrier. So you can think of this as being that barrier that's stopping them from coming together. And if they have a high enough temperature, they can still break through. But it is still temperature dependent, and it still depends on the size of the atoms, but now it's a slightly different equation. And so if we put in the numbers, we can figure out that for hydrogen, so Z1 and Z2 are both 1, these are all constants. M is the mass of a proton, E is still the charge on an electron or proton. This is Planck's constant, this is the Boltzmann constant. The only thing that's really changing in here is the atomic numbers. And so we can put them in for just hydrogen and we get about 15 million Kelvin, which is the temperature of the center of the sun. So we can make fusion happen. See here that what we're going to get is, if we put in helium, for instance, now Z1 and Z2 would be 2 each, but each one is squared, so it'd be 4 times 4, which is 16. So it's actually increasing the temperature by 16 in order to get helium fusion to happen. And as you go up in elements, it gets higher faster than it would in our original calculation. And we're going to end there for this video, and we're going to look into different ways of making elements and where that happens in the upcoming videos.